This is a data regression exercise with MATLAB using fmincon as the solver. We're going to fit some of this data right here, xm and ym, to a correlation. In this case, it's going to be y equals p1 plus p2 divided by x plus the natural log. Okay, this is going to be the natural log times x times p3. So we have three unknown parameters, and we want to come up with the best parameters to be able to minimize a normalized sum of squared errors. So our objective is going to be to minimize the y predicted minus y measured divided by y measured, and then we'll square that, and we'll sum up all of the different measurements from I equals 1 to n. So this is going to be our objective. We're going to minimize this by adjusting the parameters p. So let's set this up in MATLAB. We're going to just use fmincon. I'll create a new script and run through this with you. If you want to, you can download this source code, follow along. Just go to this link right here, and there's a tutorial on linear and polynomial regression, a one with APM MATLAB, and then I'll post the source code for this right below. Okay, so I'm going to come to MATLAB, and I've got on my desktop, I'll just go ahead and create a new script file. And the very first thing that I like to do with MATLAB is just do clear all, close all plots, and then clear the screen. And then we're going to just go ahead and copy in this data file, or this, you can either be importing it from a data file, or you can get it from, like this, just copy in xm and ym. Okay, so I'm going to come back to the script, and there are my data points. Now these triple dots right there, that just means continue on to the next line. Okay, and then let's go and just plot this. Let's see what this data looks like. And so I'm just going to do xm and ym, and I'll do red dots for that. Okay, saving this, we'll call this regression.m, and just put it here on the desktop. Okay, so let's make sure we have our data imported, and this is what we're going to be using to fit our parameters p1 through p3. So maybe the first thing that we want to do is just go ahead and create our correlation to be able to predict y. Okay, so y is going to be, y predicted is going to be, I'll just create an anonymous function here as a function of p, so it can just be inline, and then I'll do p2 divided by xm. Now when it's a vector of values that you're going to be inserting here, you need to do the dot. Okay, so it'll do an element-wise operation on that, and then return a vector of values. And okay, so then I'm going to have plus p3 times, and then the natural log in I'll do the dot times, and the natural log is just log xm. Okay, so there's my function. And so if I just come up with some guess parameters, okay, I'll just say those are going to be equal to 1, 1, and 1, okay, for P1, P2, and P3. And if I just plug those in here, I'll do hold on to that plot, and then just plot XM and YP, substituting in XM. Okay, and let's make a blue line for that, and then show that fit. Okay, so those are just our initial guesses, and it looks like it didn't do very well. I'll do X's there. Okay, we're quite a bit off from the actual measured values. So we're going to adjust the p-values now to get closer to the values that match the model and measured values. Okay, so let's go ahead and just add a legend here, and this one is going to be measured and predicted. Okay, and then I'll also do a y label, and that will be y, and x label, I'll have that be x. Okay, so let me just plot one more time to see what we come up with. Okay, so just make our plot, be able to distinguish between those different ones. Okay, now we want to use fmincon to optimize this, and so we're going to have to first of all create our objective. You can name that variable anything you want. This is just going to be another anonymous function as a function of p, and that's just going to be equal to, I'll do the sum later, it's going to be yp as a function of p minus ym, and then that's going to be all in parentheses. Okay, so if you remember from this, there is our objective right there. I'll go ahead and just resize this a little bit so we can see it. Okay, so there's our objective that we're going to be minimizing right over here. And so then, let's see, I'll put this in parentheses right here, and then divide by, and I need to do the dot, and then divide by ym. So you do the dot, so if you substitute multiple values of ym, or have multiple values of yp, it'll go element-wise on that. So multiplication, division, or something to the power also needs to have that. Okay, so that's also going to be dot to the power of 2, so that's going to be squared in that case. And now that's going to be a vector of values, but the objective needs to be just a single value. So I just need to sum up all of those values into a single objective. Okay, so there is my objective, and if I just print, let's do this, objective, okay, and that is going to be, I'll call this my initial objective, and then we'll do num to string, and inside there we're just going to print our objective as a function of p naught. So let's just go ahead and print the initial objective, and then at the end we'll also print the final objective and see how much better we did. Okay, so I have an unbalanced parentheses there. Looks like I'm missing a closing parentheses there. Let's run it one more time, and let's see, no figure to print. Okay, so it looks like I need, oh, not print, display. Okay, so there's my initial objective, 1.02. So I want to try to minimize that, and I could either adjust these values myself. Maybe I said that is too high, and so I'll evaluate it again and say, well, maybe I got my objective function changed a little bit. You can continue adjusting that until you get it about right, or you can use a solver to do that for you, like fmincon. So I'm going to just show you how to do that with fmincon. We're going to say that our new parameters, our optimized parameters, I'll do popt equals fmincon, and then we give it the objective. Okay, objective function, I just called that objective, and then we give it the initial parameters p naught. Okay, and there are our optimal values. Okay, and then what we're going to do is just I'm going to go ahead and, let's see, this is, okay, these are a function of the p naught. I've got this wrong here. Okay, that should be p naught there in yp. Okay, let me try this one more time. Okay, so this is, okay, these are a function of the p naught. I've got this wrong here. Okay, that should be p naught there in yp. Okay, let me try this one more time. Okay, so this is, okay, these are a function of the p naught. I've got this wrong here. Okay, that should be p naught there in yp. Okay, let me try this one more time. Okay, so there is our correct correlation. Okay, this is our initial objective right there, and that's how it performed. I had xm there. It should have been p naught because this is a function of p, not xm. And so what we're going to do is then have our optimal. Okay, so this is our initial predicted, and then here is our optimal predicted. And let's add one more plot here. I'm going to make those maybe squares and make those green squares. Okay, and that's going to be, instead of p naught, it's going to be p opt instead. That came from fmincon, from optimizing this. Okay, so you can see that you know, it's lining up with the measured data. We've optimized the values of P1 through P3 to get good alignment with our data. There was our initial guess value right there. So you can see it's off, and fmincon was able to try different values in an intelligent way to get those the measured and the predicted values to line up. So let's just get our final objective after fmincon, and fmincon will also produce this value, but final objective, and then if we just do p opt, then we'll print out our final objective, and then we can also display our optimal parameters. Okay, and we'll just print p opt as well. Okay, so there's our plot again, and we have our final objective, which is much better than our initial objective, and then we also have these optimal parameters right here. Okay, so I want to just share with you one other thing on how to add a constraint to this. So if you want a constraint, there's a couple additional variables or parameters that you need to put into fmincon. So I'm just going to copy in some of the more complete documentation here for fmincon. So that's the kind of the simple way that we used it, with just the initial parameters and the objective function. But if you want to access things like upper and lower bounds, you know, and other things that are in fmincon, you can do that by just going to have p opt equals fmincon there, just like we had before. But then we can also have matrix inequalities. Okay, so that one, I'll just go and write some of these out. So the A, it's going to be AX less than B. I believe it's less than B. It might be greater than B. You'd have to check on that. But that's our inequality constraint. You can put in an A matrix, you know, of some size, and then the B matrix need to have the same number of rows on that, and it'll add those linear inequality constraints. And then you can also have the equality constraints. Okay, like that, and that would be your A, E, EQ, and then your B, EQ. Most times those are just, you know, null, or they don't have anything in them, so you can just give them these empty arrays right there. And then if you want to add lower and upper bounds, then that becomes these final parameters right here to fmincon. So let's say I had this correlation, and I knew that one of these parameters, you know, for example, should be maybe this middle one. Okay, I want all of them to be less than 1.5, and that one is violating one of my constraints. So I'm just going to say that lower bound equals 1s of length 3 times 0. Okay, I'll do 0.2, and then I'll do 1s 3 times 1.5. So I've given it a lower bound of 0.2 and an upper bound of 1.5, and let's just see how well this does in terms of optimizing these parameters with those parameter constraints on there. So I'm going to run it one more time, and you can see that all the values are within those ranges. I was still able to get a fairly good final objective, but it was able to, it reduced, it's always going to make the objective function worse with some constraints, but really not that much worse. Okay, you can see it was able to adjust one of the other parameters to compensate, and so we were able to still get a good fit even with some of those constraints. Okay, so that's how you add lower and upper bounds to your decision variables. In this case, those are the parameters, and this is just from the documentation. You can also add things like nonlinear constraints, and I have another tutorial on that if you're interested. If you just come to let's see, optimization, this shows a little bit more on how to use fmincon with nonlinear constraints. You just have to create a separate function, and then you can add equality or inequality constraints with that nonlinear constraint argument. Okay, so this kind of finalizes the tutorial on regression. We've done this is essentially a linear regression because it's linear with respect to the parameters, and you have some 1 divided by xm. You could always transform that into a new variable like ym or zm, and then this one you could transform into like wm, and then it would be just parameter 1 plus parameter 2 times ym plus parameter 3 times wm, or zm and then parameter 3 times wm. So this is really just a linear regression, but it's very easy to put in a nonlinear function there. It's nonlinear with respect to the parameters, and it would also try to optimize that. So this is applicable for linear or nonlinear regression, both of those. Okay, I hope you've enjoyed this tutorial, and there's lots more content on that website and more coming up as well.